Hello, everybody. A very, very warm welcome to this session. I'm Gareth Mitchell, and I'm your friendly moderator for today's Frontiers in Science deep dive. And it's fantastic to see viewers from 69 countries joining us. And that includes a great turnout from universities, international research institutes, and many companies in chip manufacturing, tech, and R&D. So whatever your time zone, you're in great company. Welcome along. Now, if you're new to Frontiers in Science, then let me tell you, this is our flagship multidisciplinary open access journal at Frontiers. And we publish exceptional peer-reviewed lead articles on transformational science, key to accelerating solutions to the global challenges facing all of us and our planet. And we publish these articles across unique hubs with content to suit all kinds of audiences. So that extends our reach and impact for people engaged with science, policy, and society and beyond. To date, we've published 29 hubs spanning over 110 articles covering a diverse spectrum of transformational science. The research has been cited over 1,100 times, it's been viewed over 3.7 million times, and we regularly get picked up by the media. Today's deep dive focuses on this lead article, Breaking the Memory Wall, Next Generation Artificial Intelligence Hardware. And that work is led by Professor Kaushik Roy. And we're very proud to give the article and its hub a home here in Frontiers in Science. Now then, if we were designing computers from scratch to accommodate today's artificial intelligence revolution, we wouldn't come up with the architecture that we have now. It seems quite clunky when you think about it that our machines are constantly having to shift data between the memory and the processor, and that consumes time and energy. It seemed, of course, a good idea 80 years ago when John von Neumann pioneered the stored program concept in the 1940s, and it's served us very well. Of course it has. I mean, look how far we've come since the days that even I'm old enough to remember, when it took a whole room full of cabinets to achieve anything like what our laptops or our smartphones can do today. But with relentless advances in AI, it really is time for a new way of thinking. So say the authors of the paper we're discussing today. We need to bring the processing to the memory, compute in memory. You'll hear that phrase a lot over the coming 90 minutes or so. And that's just one way towards smarter, more efficient AI, artificial intelligence that is more human brain like. That is how we're going to overcome the memory wall. And that's another phrase that will come up a lot. It's in the title of the lead article, of course. In an era when we hear so much about algorithms, today's story is about hardware. And yes, of course, we will talk about the code that runs on the hardware, but a lot of our conversation in this session will be about novel hardware inspired by biology. We're taking you to the device level today, and I have to say, for an electronics graduate like me, it's a very exciting place to be. But before we fully get going, I just want to show you around a little bit. So this is the article hub, and alongside the lead article, we also have an editorial by Professor Richard Stanley Williams of Texas A&M University, it's also on our panel today. Then we have a policy outlook by Vilas Dar of the Patrick J. McGovern Foundation. Also on the hub is a very useful lay explainer, and we have a video, and there's even a version of the lead article in Frontiers for Young Minds. That's our science journal for kids. So there you go. That's the hub. There's loads on there, so do check it out. As for today's session, here's the schedule. This is how it's going to go down. First, we're going to hear from two authors of the lead article, Professors Kaushik Roy and Arijit Ray Chowdhury. And then joining us for the panel discussion are co-author Dr. Tanvi Sharma and Professor R. Stanley Williams. And that's all coming up. So let's get into it and say hello first to Professor Kaushik Roy, the Edward G. Tiedemann Jr. Distinguished Professor of Electrical and Computer Engineering at Purdue University. A pioneer in low power, very large scale integration and cognitive computing. He has supervised over 75 PhD graduates and co authored two seminal books on low power CMOS VLSI design. Kaushik has been recognized with all kinds of prestigious honors, including the Humboldt Research Award and the US Department of Defense's Vannevar Bush Faculty Fellowship. More recently, he was awarded the AIoT Pioneer Award at the 19th edition of IC Edge, hosted by the Indian Institute of Science. So, Kaushik, thank you very much again for bringing this article to Frontiers in Science. We're going to kick us off. Over to you.
All right. Thanks, Gareth. All right. So let me start with the evolution of AI. Neural networks are certainly not new. They've been there for a long time. But back in 2012, with the convergence of data, availability of data, the compute performance, and of course, better algorithms, that triggered the new era of AI. If we fast forward to 2018, that's the era of large language models and generative AI. So what you can see is that since then, every year, the model sizes are growing and growing at a much, much faster pace than Moore's law. For example, the transformer sizes are growing at 750x per 2 years compared to Moore's law, which is about 2x per 2 years. But that has led to also help us in delving into applications, which, for me, I've read in science fiction. A few days ago, I actually saw a couple of articles in BBC, and one of them was on how long until a robot is going to do your chores, household chores. And those are the kind of things that we have read in, science fiction. But today, it's certainly possible. Now, a couple of years earlier, there was an article in CNN, which actually showed that AI won an art contest, and the human artists are furious about it. So, the prediction of AI going forward is that the models are going to get larger and larger, and with that, the power consumption is actually going to go through the roofs. The power consumption is going to go through the roofs, and AI has certainly started, as we can see, has started pushing the limits of energy, chip production capacity, and data. So if I have to go a little bit further and go into a little more details of the energy cost of AI, so we did an analysis of the operational energy use of AI chatbots. And with assuming that we have 2 billion users and each user uses 5 queries per day, and there are 365 days a year, turns out if each query consumes takes about 0.001 to 0.01 kilowatt hours, then the total watt hours turns out to be 3.65 to 36.5 terawatt hours. A dam usually typically produces about 2 to 10 terawatt hours, and if I were to convert that into how many dams it's going to be for, in this particular case, Hoover dams, that's equivalent to 5 Hoover dams. That's a huge amount of consumption. On the other side of it, if I were to think about the energy cost of AI and looking at, we did a case study on a smart glass where you can actually, using the smart glasses, you can recognize objects or humans. We did an analysis of it, implementing a RetinaNet DNN algorithm on Google Edge TPU, which shows that the battery life, without going into the details of it, the battery life under ideal conditions is about hours. So if you now consider, for example, display power and so on, it turns out it's going to be possibly less than half an hour. So that's kind of unsustainable. On the other side of it, if I were to compare with the biological systems, despite the tremendous progress that I talked about in AI, biological systems still possess a level of functionality that is unmatched in artificial systems. And we did some work actually with IARPA, where our proposal was to actually fly like a fly, a fruit fly, let's say. So if you were to consider, for example, a fruit fly, it has about 100,000 neurons. It does amazing stuff, right? Dodge dynamic obstacles and avoid obstacles in cluttered environments and so on. And they do that with about microwatts of compute power. But on the other side of it, if I were to think about the UPenn flying monkey that we developed as a part of this project, the power consumption or the energy, or the power consumption for the compute was about 1 to 2 watts. So if I go further and look at, for example, go higher up the chain, go from fruit fly to, let's say, dogs and humans. The humans, it turns out, does amazing stuff that we do with about 20 to 30 watts of power consumption. Whereas if I were to use these data centers to play, for example, the game of Go, that required about 10 to the 6 watts or so. So it's not even a comparison. So when we try to compare, for example, AI versus natural intelligence, there exists a huge efficiency gap. Now, in order to really talk about all the different applications that we actually mentioned earlier, there's been an evolution of the AI models. It started with multi-level perceptrons to convolutional neural networks. Again, depending on the applications that we look at, spiking neural networks, RNNs, transformers, which are the backbone of today's large language models, into neurosymbolic AI that Arijit is going to talk about. And on the other side of it, in order to actually handle the computations here, and most of the computations being in this particular case for all these application domains of the workloads, for speech, language, vision, it's basically the matrix multiplication. We end up doing a large number of those. There are other also operations that we need to do, tan hyperbolic, softmax, and all, which I'll get into that later on. Those are actually quite important for these large language models. But in order to handle some of these large-scale matrix multiplications, there's been an evolution in the AI, in the hardware. In particular, actually, the evolution from CPUs to GPUs to tensor processing units and NPUs and all has happened. However, if I were to look at all those, if I were to look at the hardware flops over the years, that's been steadily improving over the last 20 years or so. But on the other side of it, if you have to compare that with the DRAM or the interconnect bandwidth, that's lagging, as you can see, far behind. So the point is that there's a need for really thinking about new architectures, new hardware, and what should those hardware try to do? Really take care of some of the inefficiencies that exist today. Most of the applications would require, for example, heterogeneous processing. So heterogeneous processors are going to be important. They might have to deal with sparse and irregular access patterns, high memory intensity, or in other words, talking about the memory wall, can we alleviate this memory wall? And then finally, I mentioned some of these things on softmax, tan hyperbolic, and all. And so those have to also do transcendental functions in an efficient way, so that I can reduce that efficiency gap that exists today. So now let me get started with an example cross-layer design. In this particular case, I'm going to talk about drone navigation. And so to that effect, if a drone has to go from point A to point B, as an example, it has to figure out what path it should take. Are there any obstacles in its path? Are there any moving objects in its path? And can they estimate how it's going to be moving and so on? So to that effect, it has to know the environment around it, which is the optical flow. It has to do depth estimation, segmentation, object detection and tracking, and so on. And finally, after it's done that, it figures out a path to go from A to B, and then, of course, apply the proper controls to its motors to be able to go there. Now, in order to do that, if I were to just use only vision sensors and nothing else, then let's start with, for example, a camera. And the two different kinds of cameras we can potentially look at. One is the standard frame-based camera, and other is an event camera. The event camera is really bioplausible camera, when there's a relative motion between the camera and the object, then there's a spike that is produced. And the spike really depends on a positive spike or a negative spike, depending on the intensity changes that you get. Now, of course, the input coming from the camera then has to go into a processing unit, or in fact, it's going to be processed by some neural network. They could potentially be the standard deep learning networks, or could be ANNs, SNNs, the spiking neural networks, could be LSTMs, or could be, in fact, transformers, or could be a hybrid combination of some of these networks. And we'll go into that hybrid combination in a few minutes. And then finally, at the end of it, these algorithms and these network architectures have to be implemented in an efficient hardware. So with that in mind, let's try to analyze and see what's kind of algorithms that we need to have. And that will determine the kind of architecture or the hardware architecture that we need. So what we did is we actually looked at optical flow, an important problem for all these applications. And what we implemented this optical flow in a completely fully deep learning model, ANN. And what I really wanted to underscore here is that fact that the average energy consumption in this particular case, which I'll compare it with the other implementations, is about 24.5 millijoules. And the average AEE, which is the endpoint error, is about 4.77. I mean, these numbers are really for comparison purposes. On the other side of it, if I were to implement that in a completely fully SNN model, in this particular case, it's actually a fully SNN model which implements this the optical flow. Turns out there's a little bit of decrease in the average endpoint error. Lower is better, but however, there's a huge amount of improvement in energy consumption because now I'm able to use a model which is with the fraction of the number of parameters that I use, for example, in a fully ANN implementation that I showed earlier. Now, the reason why we're able to do that is because we're able to capture the timing information effectively using the spikes that are coming in from the inputs. And the spike information is stored in the membrane potential, the timing information, and that helps us in actually doing sequential operations like optical flow. On the other side of it, if I were to think about SNN, ANN hybrid, that in this particular case, actually with 13 million parameters, it actually does better in terms of the average endpoint error. The energy consumption certainly improves compared to the one that we had earlier with ANN, but certainly larger than the very lightweight model that I showed earlier. And then finally, I just wanted to show that if you are able to use a sensor-fused SNN ANN hybrid, which actually takes the best of both worlds, taking the event camera inputs and the grayscale camera intensities that comes together. And if you can combine them together effectively, turns out you can actually get the best endpoint error. In this particular case, it's actually 2.9. As I said, lower is better. And the energy consumption is also better, but now uses about 7.5 million parameters. So again, showing that these hybrid kind of implementations can potentially be good in a lot of applications. Now, what kind of implementation should I have? What kind of hardware should I have for implementing some of these? So to that effect, what we did is we actually looked at the hardware fabrics, and we also remember that I showed earlier that the matrix multiplication are absolutely important. And at the end of it, some of the other functions, in particular the exponential functions leading to softmax, tan, hyperbolic, and sigmoid, those are also important in these neural networks. So the hardware architecture, ideally, that we'd like to have is that can efficiently implement these algorithms, and in particular these important functions, as I showed. And then they can potentially embody the computing principles of the brain, but that's not required. At least we know that brain is quite efficient. So if we can actually mimic some of these operations, maybe we can get an energy advantage. So the GPU systolic arrays, they can certainly implement some of those. We can bring in quantization, sparsity. Those are available in some of these networks to be able to implement them better. Memory architecture plays a very, very important role, and to the effect that, hey, if I'm able to do some of these computations very near the compute elements or in the memory itself, then the data movement cost can be improved and I can potentially get a large improvement. There are other kinds of approximations that one can use. I mean, can potentially use stochastic hardware in some class of applications. Quantization is a form of approximation that one can use. And then at the end of it, rather than using, for example, CMOS devices, one can potentially also look at other kinds of neuromorphic devices and interconnects. And then for some of the applications like using SNNs, potentially think of event-driven computation. So to that effect, let me get started with matrix vector multiplication computations. And just to give you an example of it, I'm showing a memory, a standard, let's say a memory that I'm showing. And in general, the regular memory operation would turn on one word line. And with the peripherals like simple sense amplifiers, you can read what you're trying to read from that particular word line. Now, going a little bit further, one can do in-memory digital computation by turning on, in this particular case, 2 word lines. And you may not want to do that directly in a 60 transistor cell, but with some modifications to it, it turns out you can actually turn on some of these word lines, 2 word lines together to be able to do AND operations, XOR operations, and so on, by changing these peripheral circuitry slightly. Now, going further, if you're able to turn on multiple word lines, one can do analog computation in such a memory. And such computations are done in the analog domain. And to that effect, the interface circuitries that I'm showing at the bottom, which are the peripheral circuitries, need to be a little more complex. You need to have digital to analog, analog to digital conversions. Now, going further, you can certainly use, for example, the standard SRAM cells for some of these computations or non-volatile memory. And later on, we'll see that in order to implement some of these transcendental functions that I mentioned, exponential, softmax, and others, one can also embed at no extra cost a ROM on top of these RAM. Now, with that in mind, this is a very simple example of a matrix vector or matrix multiplication that I'm showing, where I'm showing a crossbar architecture where at the cross points you have a conductance element, and these conductance elements are represented by could be with CMOS, but could be also with RRAMs, PCMs, STT, MRAMs, and so on. Again, most importantly, what you're going to get is, if you have these inputs which are coming in, which are voltage, the output that you get are summation of VI times GI, which are the dot products. And now what one can do is, you need, as I mentioned earlier, those interface circuitries. Could be multiplexer, sample, and hold circuitry, but more importantly, an analog to digital conversion, so that now I'm able to communicate with other, logic blocks of the circuit. Now, it turns out that these, if it's an analog computation, these interface circuitries can take up a good amount of area and power consumption. So, a potential architecture one can think of, and it's a simple-minded architecture that I'm showing, where I have these matrix vector multiplication units replicated into these tiles, and each of those tiles have really a large number of other kinds of computations, logic computations, maybe also some memory in there, and they can be connected in a NOC kind of architecture. Now, for such an architecture, you also potentially have a high density of chip memory. And finally, what we did is we did an analysis of such an architecture, implementing large-scale neural networks in such a spatial architecture. And it turns out you're dominated now by this interface circuitry cost for these analog computations that we're talking about. Then the next slide, this slide shows basically a potential hardware architecture using basically the crossbar cores that I showed. So each of those cores basically form connected together, form a tile, and those tiles can potentially have shared memory, as I mentioned, instruction memory, and so on. They can be all combined together. Now, going beyond that, one can also use, for example, transcendental functions for computations. And this is actually showing it with an architecture where it overlays a ROM into the RAM. And without going into the details of it, the difference in this architecture, this actually uses a magnetic tunnel junction with word lines and the source lines of the bit lines. The main difference is that I have 2 bit lines as opposed to 1 single bit line. And the magnetic devices are connected either to bit line 1 or bit line 0. And depending on how it's connected, either to the bit line 0 or bit line 1, is the ROM data that I have. On the other side of it, the RAM data in this particular case is going to be stored as an AP, anti-parallel or parallel combination configuration of the magnetic devices. And that's basically the RAM data that I have in this particular case. Really the configuration of the MTJ, but the ROM data in this particular case is basically whether it's connected or not connected to bitline 0 or bitline 1. So using that kind of architecture, again, not without going into the details of it, one can do RAM operations by activating, a bit line, RAM operation by activating both the bit lines together and reading it accordingly. The ROM operation requires you to actually activate one of the bit lines, and depending on whether it's connected or not, you're going to read actually a 0 or a 1, whether it's connected or not connected to the MTJ by reading one particular row. And finally, this particular architecture can also do the MVM that I was talking about, the matrix vector multiplication operations, by actually, again, activating both the bit lines. But then again, in this particular case, I'll have ADCs, TIAs, and the shift and add interface circuitry that I just mentioned earlier. So going further, this is basically computations that I'm showing, for example, on chip, but it's also possible to do computation in a DRAM. And again, by doing majority functions, one can do add operations and so on. So what one can do in a DRAM is that you can keep some compute rows and some data rows, and you can write into these compute rows. And by turning on multiple rows in that compute row, you actually are able to do, for example, add operations and so on, which can be used in, computing in the DRAM itself. So going back to the vision-based navigation that I mentioned earlier, now, and analyzing what we can do, we implemented optical flow in the NVIDIA Jetson TX2 architecture to show what the inefficiencies are. And in this particular case, our implementation showed that we could get about computation about 7 to 8 frames per second. On the other side, and that doesn't meet the requirements that we needed. And these are actually the hybrid ANN SNN architecture that I talked about. Now, going further, it turns out that one can potentially use now in-memory computing. In this particular case, we used it adaptive SNR, sparsity-aware compute in memory. And using that in the architecture, turns out you can actually get now 30 to 31 frames per second. Going further, we actually also used a neural network architecture with in-memory computing that also provided the kind of in-memory computing for also the membrane potentials, able to get about 30 to 35 frames per second. And if you go further, which Arijit is going to talk about, is crossbar-based RRAMs and all. It turns out it's possible to get even better efficiency. So going further, and if I were just to end it, the one question that one can ask is that what kind of, if I were to do in-memory computing, and then the question, of course, is then what kind of in-memory computing should I do? Digital, analog? When should I do it? What kind of application is suitable? For example, should it be compute-bound, memory-bound, and so on? And finally, at the end of it, where should it be? Should it be in the DRAMs? Should it be in the register files or L1 or L2 caches? Or should we at all do compute in memory? So with that in mind, one can potentially think of a heterogeneous, memory-centric heterogeneous accelerator, which is flexible, versatile architecture. And I'm going to end with that one can potentially think of these chiplets doing on-chip acceleration, which are put on a packaging substrate. You can also have an HBM as an example. And the HBM can also have compute in there with a logic die in this particular case. You can potentially think of this on-chip accelerator to have SIMD, spatial processor with SIMD units, or could actually be compute in memory, and there could be analog or a digital compute in memory. And with that in mind, one can potentially think of applications where you can try to say, hey, can I take these large scale applications, and you don't have to have one sim accelerator, you can have multiple of those or doing different kinds of acceleration. But what one can now think about it is that, hey, if I take a large scale, large language model, and if I have to implement it, one can figure out, hey, the mapping is going to be very important. So one quick way of doing that would be to look at, for example, what's called the pre-fill phase, where in an LLM, it turns out 50% of the execution time is dominated by GEM operations, which is matrix multiplication operations. But in the decode phase, it turns out that one has about 90% of the execution time dominated by accesses to the DRAMs. So with that in mind, one can actually do proper phase-aware mapping, and that potentially gives you a good amount of improvement. So the kind of architecture, generic, flexible architecture, I believe, somewhat like this, is going to be possibly an AI hardware architecture of the future.
That is great. Thank you very much indeed for that. It was absolutely fascinating, and I love that kind of background. That in a single presentation, we've gone from the number of Hoover dams worth of energy needed to power chatbots and AIs, all the way through to the really striking energy gains that you've made and energy savings with this SNN spiking neural network approach, talking about implementation and then some of the applications as well. So yeah, it's amazing stuff. Thank you very much indeed for that. Okay, up next is Professor Arijit Ray Chowdhury, who's a professor in the School of Electrical and Computer Engineering at the Georgia Institute of Technology. And Arijit holds over 25 US and international patents, and his work's been recognized with multiple honors, including the Intel Labs Technical Contribution Award and the Semiconductor Research Corporation's Technical Excellence Award. Arijit is a senior member and distinguished lecturer at the Institute of Electrical and Electronics Engineers. And he's here to tell you what he brings to the table. So over to you, Arijit.
Thank you so much, guys. Thanks a lot. So I'm going to take the last part of this presentation and talk a little bit about some of the silicon work that we have done to understand, implement, and prototype some of the memory-centric AI architectures. So if you look at neural network accelerators today, and if you look at one of the large bottlenecks, like Kaushik was saying, is the ability to store a lot of data, because you need a lot of memory systems, memory subsystems, to be able to store not only the neural network weights, but also the intermediate values, activation functions, and so on. So there has been this push for higher density and higher capacity memory, particularly if the memory is on die, that you can integrate along with your logic. And the logic can be a CPU, a GPU, or some sort of an XPU or a neural processing unit. But no matter what you have, you will see that more than 50%, 60% of the die today is just memory. The workhorse of the semiconductor industry is, of course, the SRAM, which is a 6-transistor cell. It's a very mature, it's a mature product. We scale it down all the way up to 3 nanometer and 2 nanometer today. One of the advantages it has is, of course, it has very high endurance, and in terms of read and write speeds and energy, it gives you some of the best metrics that you can think of. The only challenge with SRAM is that it's a pretty large cell. So if you want to integrate more memory on the same die, you'd want to build your memory array based on a technology which has a smaller footprint. So one of those technologies is the RRAM, or the resistive RAM. And we have been working very closely with TSMC over the last almost a decade on understanding RRAM, prototyping, and then building prototypes and measuring them. And it's one of those memory technologies which has very high density. It gives you a very high capacity, but it comes with its own challenges. For example, it is difficult to write. You need typically higher voltages to be able to write. Its endurance cycles are also lower, and so on. But the advantage of using RAM or any kind of resistive memory in a neural network or an AI accelerator is the higher capacity of memory that you're going to get. And the in-memory computing, particularly the analogish, mixed signalish in-memory computing that Kaushik talked about, you can actually implement that pretty efficiently using an RAM kind of a technology. There are also other technologies on the horizon, particularly for memory. MRAM or magnetic RAM is something that Kaushik mentioned. This is again one of those technologies which has shown a lot of promise. PCM or phase change memory has been around for a while, which again poses some challenges in terms of endurance and write energy. Ferrofets is a new genre of energy which has been investigated, in academia and industry quite actively. It has a lot of the good properties of SRAM along with the scalability of some of these resistive memories. And on top of this, resistive memory structures, we have had eFlash, which is embedded flash or embedded DRAM for a long time, which are charge-based structures. No matter what kind of memory element that you choose, at the end of the day, if you want to do in-memory computing, you have to understand the physics or the analog behavior of the memory itself, and understand how do you make it more reliable when you abstract some of its properties at the digital layer or at the programming layer. So if you look at how resistive memories and RMs in particular can be read, I'm just giving you an idea of how the read structures have to be changed. So if you think about reading an RM memory in a in-memory computing kind of an architecture, you can either do it with voltages, which means you, for example, charge a capacitor and let the capacitor discharge, and you look at the voltage, the VBL, which is the bitline voltage, and understand how much it has discharged, depending on how many of these resistive structures, which are shown here in blue, are turned on versus how many of them are turned off. On the other hand, if you are a little more creative and you want to use a current mode structure for reading, it gives you more robustness. It is a little more complex in terms of its implementation because you have a feedback loop and the feedback linearizes and typically nonlinear behavior. But as you can see that the system becomes more and more complex as you try to read some of these memory elements with massive parallelism. And that's what I want to convey, that that read and sense structures become more complex, and a lot of the complexity goes down the stack into the circuit level when you try to expose them for efficient AI applications. Two sources of read error, for example, one would be the IR drop that you'll see on the bit line and the source line that starts becoming a problem, and you end up with gain errors. You may also have offsets, like offset from the current from the transistors which are already off in the memory array. That gives you offset errors. Again, just two examples of errors that you now have to worry about, that you don't have to kind of think about when you are designing a regular memory without in-memory computing. But once you start embedding computing in the memory structure itself, there are new kinds of foundational errors that will show up that you now have to design for. So for these two examples, for example, an IR drop error or an offset error, we worked on a variety of schemes, and the one that works pretty well is to essentially move away from a two-terminal sensing that we do for memory to something called a four-terminal sensing, which is also called Kelvin sensing. So it's a way to sense voltages without actually injecting current, and we were able to embed some of them into TSMC multi-project wafer vehicles that we had access to, and we found that these kinds of advanced sensing methods can actually give you the high accuracy that you need to build in-memory computing elements that can eventually go into neural networks and spiking networks. Similarly, for offset currents, we introduced a combination of digital and analog calibration. And calibration allows you to remove the offset voltages and currents that you'll get from the non-accessed rows of the memory array. And by doing that, you can actually, again, recover a lot of the accuracy loss that you will otherwise have. And this is just measure results from a pretty large prototype of a chip. This is actually a large 36 millimeter square chip with a lot of RM modules, with a lot of memory, and you can see a Cortex M3 processor. So this is a full neural network processor with embedded memory and computer in a computing memory. And with all of these compensation techniques and calibration techniques, you can see that we could we could essentially achieve very high linearity, about 0.9973, and then between the panel on the left and the panel on the right, you can see without and with offset cancellation, you could make the readouts very linear, very flat. That's what you want. You want as flat them to be as flat as possible, because you're reading your output on the y-axis and your input is on the x-axis. So again, long story short, what I want to convey is in-memory computing comes with its own design challenges, which will expose a lot of the device behavior of the elements themselves, and challenges us to think about how do you efficiently do that with high performance and energy efficiency. So piggybacking on the concept of the spiking neural networks and the frame cameras that Kaushik talked about for optical flow, this is an example of bringing all of this together in an in-memory computing platform where you have an image frame-based pipeline, where you have on the top you have a convolutional neural network, and then on the bottom you have an event camera with a spiking neural network. So the idea here is that a frame-based camera, which is a regular camera that we see, that gives you very high spatial resolution, right? You can see things very, very clearly, but they give you very poor temporal resolution, because you can only sample things at 30 frames per second or 60 frames per second. Whereas an event camera is essentially capturing changes in intensity. So it gives you an equivalent of 1,000,000 frames per second, but it does not give you the spatial resolution that you need. So if you look at biomimetic systems like the eyes of, let's say, eagles or other kinds of predatory birds, they have this amazing ability to kind of find a prey with a very high spatial resolution. And once you find that prey, it can lock into the prey and have very high temporal resolution in its eye to be able to track. So that was exactly the problem we are trying to solve, which is identifying a target and tracking. And we were trying to see how you can do that in a memory-centric way using these parallel pipelines of CNNs and SNNs. So on the top you can see that that there is a picture of a virtual environment of a CNN solving the problem in the CNN domain. On the right, on the panel, which is currently dark, that's an SNN, and the spiking neural network is working on the frame camera, and it's producing trajectories for operation. We took that concept further and essentially built a full system architecture around it with on-chip memory, RRAM for in-memory computing, RRAM-based processing elements, and an array of spatial processors to be able to solve this concurrent problem of SNNs and CNNs. And in a real world demonstration, you can see that when we embed that into an actual system in a drone, you can see that on the left there's the images from the image camera, the frame camera, and on the right you see the spiking neural network working on the event cameras. And what you get as a result of that, you get the best of both worlds. If you look at the chart with the CNN, the red dot, you have very high accuracy because you have very high spatial resolution, but low latency, or very high latency, so low speed. Whereas the blue cross is essentially a spiking neural network, which gives you lower spatial resolution, so lower accuracy, but very high speed or very low latency. And by combining these kinds of pipeline units in a memory-centric architecture, you can get to this green spot, which gives you very high target acquisition ability, as well as the ability to track any kind of targets. So as I look at the future and the future of embodied platforms, we are going to see more of these kinds of juxtapositions of spiking networks, CNNs, different kinds of modalities of sensing. And the future of what is called physical AI today rests on the idea of having a memory agent with multimodal sensing, some sort of a planning agent which can be based on a language model like an LLM, or there has to be a reasoning agent which can be either a neural model or it can be a symbolic model, and then you can have some sort of a control and execution. So the future looks more and more like this kind of a platform where you have a very tight integration of memory with logic that allows you to not only perform actions, but also think about actions, be reflective, and be more thoughtful and planning. And you can think about this being augmented with communication agents, where AI agents would be able to talk to other agents as well as humans. And this is a prototype that we recently built on neurosymbolic. So this is the idea of building neural and symbolic algorithms together. So this is where we have this prototype that we recently built using neurosymbolic AI for embedded applications. And the application is again in the area of physical AI or embodied AI, where you embody the AI with a physical structure. Again, without going into the details of all these applications and what these mean, the idea is to be able to perform not only from sensing to to activation, that kind of a pipeline, which is often called a system one pipeline, but also augment that with a process of thinking and reflection, which is often called the system two pipeline. As we look at these memory-centric architectures, including in-memory computing, there are many challenges that will continue to remain in a circuit or a hardware design kind of a perspective. There are all kinds of non-idealities that you have to work with. Reliability always is a concern. The write cost for many of these non-volatile memory structures is pretty high. Building data converters, data movement, design tools, all of these are challenges that circuit designers, architects will continue to face over the next decade, as we are trying to look more and more at architectures, like Gareth mentioned at the very beginning, that merge the computing and the memory together in sort of a non-von Neumannish or post-non-von Neumannish architecture to challenge us to build new kinds of systems and algorithms. So with that, I'm going to end, and I'll leave it to Gareth to take us to the next steps.
Okay, thank you very much indeed for that. And building beautifully on Kaushik's presentation right at the beginning there as well. So there we are. We've heard our first two speakers, but I think now it's time really to jump into a bit of a discussion. And that includes you, dear viewer and participant. As I was saying, keep those questions coming yeah. All the ways of getting in touch with us are right there. We told you at the top, and yeah, make it a really good discussion. Okay, so I'm very pleased to welcome our next speaker, PhD graduate Dr. Tanvi Sharma, a deep learning performance architect at NVIDIA at the moment, and co-author of the lead article that we're discussing here today. She's interested in AI accelerators, compute and memory architectures, and energy efficient inference. Tanvi earned her PhD from Purdue University in 2025, focusing on optimizing compute in memory systems, and is sharing her in-depth hardware knowledge by serving as a graduate instructor, passing on that knowledge. Her honors include the MLSys Rising Star Award and the Qualcomm Innovation Fellowship, highlighting her impact and contributions to AI algorithms and hardware designs. And now also here, just joining us for this section, is Professor Richard Stanley Williams, Hewlett-Packard Enterprise Company Chair at Texas A&M University. And he is a world-leading researcher in nanotechnology and computing, and his interests span nanoscale electronic, ionic, and photonic devices, nonlinear dynamics and chaos, cognition, and computation. And of course, many of you will already know about Stan. He's best known for pioneering the memristor and all kinds of contributions to neuromorphic and analog computing. He currently leads the Remind Energy Frontier Research Center, researching brain-inspired computing. And he's won a whole load of honors, including the Feynman Prize in Nanotechnology and the Hermann Bloch Medal for Industrial Research. But hold fire, Stan, because I'm actually going to start with you, Tanvi. And of course, we've been hearing we're facing this 5,000-fold growth now in the size of AI models. And that's all very well, but how can compact battery-powered edge devices surmount these huge design challenges? We know about the really big kind of areas, but when you have the design challenges around these small devices, and we hear about these 5-fold orders of magnitude increases in AI capacity and energy and processing demand. How's that going to work out? Over to you.
Yeah, thanks for introducing me and the question, Gareth. About your question, before diving in, I would just like to clarify that the views I express today are my own, and I'm not representing NVIDIA here. Now, about the question, from industry perspective, the battery-powered edge devices have a different line of product. So even though the main foundational models are increasing by 5,000-fold, there are two things that are driving key innovations. One is that algorithms are driving innovations in hardware. And second is hardware in turn is guiding how much you can scale the models. So if you want to focus on just the edge devices, one example could be, say, mixture of expert models. So mixture of experts model, you can scale the model size, but still it has a lower compute and memory requirement. That's an innovation from the algorithm side. Now, because we have these new kinds of models, you also need to adapt your hardware for such models. So, because say MOEs require more communication, we are now more focusing on improving the network bandwidth or increasing the bandwidth from main memory. So, I guess industry current efforts are still focused in the traditional direction of improving and scaling the architectures. But if the model size keep improving at the same scale, I feel we will move to memory centric architectures in future.
Okay, lovely. Thank you very much indeed for that, Tanvi. And so stay there because we're going to jump into a discussion. But introduced Stan just a few moments ago, of course, the pioneer of the Memristor. And Stan, you've written a really illuminating editorial for us based on this research. And in your editorial, you talk about, the great sort of economic challenges that we face here, and more to the point that really just the economics no longer compute when we're talking about, this von Neumann bottleneck, this kind of the inefficiencies we've been hearing about in traditional computing architecture. So I suppose the question for you is, you read this lead article, you hear these presentations, you've just heard Tanvi's article there. Are we finally getting over the the infamous von Neumann bottleneck, do you think?
There are obviously several viable solutions, but we're still in the era of let a thousand flowers bloom. The issue is that there have been a lot of very convincing demonstrations that in-memory computing is possible and that it has significant benefits in terms of latency and energy power dissipation. But there's there's no coherence. There are a lot of different research groups around the world trying a lot of different ways of doing this, and that's great. That's important. But the issue is we have a lot of work to go. I was actually just in a DOE workshop last week in which several speakers were talking about the growth of the energy required in order to be able to sustain the growth in AI and the large data centers that are being built. And it's clearly unsustainable. The amount the growth rate of what people are anticipating for AI is going to far outstrip our ability to actually supply energy for it. But there was another issue, and that is that 80% of power, right? I mean, 80% of the calculation or computation that's being done in AI data centers is actually inference. And that's because people haven't figured out how to do it elsewhere. So I think that this issue of especially being able to do memory-centric computing on edge type of devices is essentially going to allow the technology to spread out and to democratize and essentially load balance, if you will. But exactly what the technologies are going to be right now is still up in the air. It's an open question.
Yeah, which makes it so exciting, doesn't it? And Kaushik, can I bring you back to visual data? And you talked about that in your talk. Of course, we have frame-based models that take snapshots at regular intervals, like a camera. Well, that's how I think of them anyway. And then, of course, we have the event-based models that are more like the human eye. So I suppose the question is, how can a single CIM, compute and memory platform accommodate both those paradigms, or can it?
Yeah, that's a good question, Gareth. And as Arijit was talking about, I mean, we're talking about these cameras, and they have, a lot better. I mean, these DVS cameras have the fidelity, in some ways, temporal fidelity is huge, right? It's much better than the frame cameras. Now, you can potentially think of getting one frame, and in between the second frame, before the second frame comes, you possibly have thousands of spikes that might come in, right?
Mm.
So now one of the things that we did in our implementation is that one can certainly take advantage of some of these things in a event-based system, but we actually used a synchronous design. And so what we had to look at the resolution, the time resolution, we combined some of those together and synchronized both the, when we looked at, for example, the ANNs and the SNNs, when I combined them together, synchronized a particular internal node before it starts the decoder. So that's how we actually used it. Now, in a lot of ways, the same in-memory computing techniques can still be used because the addition that you might actually have in this particular case is that the membrane potential needs to be updated. And the membrane potential update, you can potentially do it in the memory itself too.
Okay.
So you can combine these two into sort of a hybrid kind of model where you're able to do both together. Now, you don't have to do in some cases. I mean, again, remember that it's not absolutely essential that you do compute in memory for these membrane potentials, but it does allow you to do that.
Yeah, and I guess a lot depends on the application as well, so there are lots of different factors. Okay, so we're going to go to some of our audience's questions as well. This one from Anirudh, who has this one for you, Arijit. And this is a bit of an assessment from Anirudh, and Anirudh would like to know if you agree. So in-memory computing, says Anirudh, is very appealing as a potential component of future artificial intelligence hardware. However, for LLMs, it seems that in-memory computing would only be truly beneficial if the entire model fits on the chip. Otherwise, because large language models exhibit much less weight reuse compared to convolutional neural networks and older architectures, its impact on reducing energy consumption and latency may be limited. Is this an accurate assessment? Asks Anirudh to you, Arijit.
Yeah, that's actually a great question and a fair assessment. With language models, again, I think if you look at large language models, there is a prefill stage and there is a decode stage. So the memory reuse for these two stages are also very different. So the kind of so if you architecturally speaking, when we draw what is called a roofline diagram, where your compute versus memory bottlenecks are depends on the stage of that particular pipeline that you're executing, and also the amount of memory or the capacity of memory that you have, the amount of compute that you have to do, and a whole bunch of other things. So overall, I'd say this is true that in language models, memory reuse is a little lower than CNNs, where you can actually have something called a weight stationary architecture as well, where the whole model kind of fits into the on-die memory. But then again, if you look at LLMs, there are, you can, with batching particularly, and Stan talked about inference, if you have a situation where you have when you have multiple concurrent users that are kind of accessing the same portion of the prefill stage or the decode stage concurrently, then the reuse of course goes up. So there are ways to kind of artificially or from an algorithm's perspective hide some of those challenges. And further, I'm also going to say that I just talked about on-die in-memory computing, but if you bring in DRAM, HBM, Flash, there are all kinds of ways to embed a compute, not necessarily matrix vector multiplication, but some degree of compute in those memory segments as well. So these are again ongoing research that's going on, but I would not limit ourselves to just thinking about in-memory computing on-die only, but also think about the entire memory hierarchy and how we can distribute computing across the entire memory stack.
Yeah, great stuff. Tanvi, I want to put something to you about safety critical applications. This one comes from Kasem, who asks, how do compute and memory architectures address reliability, programmability, and security concerns in safety critical applications? It's a great question, isn't it?
Yeah, it's definitely a great question. By safety critical applications, could he give some example, maybe?
I'm reading it off the screen, so I can't actually hear what Kasem is saying, but
Right.
I don't know, but I'm thinking maybe some driverless cars, possibly those kinds of areas.
Probably. Yeah. So if we think in that direction of reliability and security, I think the challenges would remain the same as there are in traditional architectures. So as we deal with security and reliability there, we can use similar circuit techniques and compute and memory based architectures as well. Other than this, in terms of reliability, I guess if you use, say, embedded non-volatile memory-based architectures, which have lower endurance, in those cases, we can potentially use some circuit techniques like how Professor Arijit was mentioning. We can reduce IR drops and other techniques to make them less error resilient. But if you are looking for an application which requires deterministic behavior, then it would be better to use, say, digital compute in memory or traditional architectures instead of switching to analog.
Okay. Yeah. No, and that would make sense as well. One for Stan here, actually. I'm not sure who the questioner is, but the question is, how does deploying AI at the edge help solve the economic unsustainability of data centers while increasing computational sovereignty in quote marks there, computational sovereignty. So question for you, Stan. Did you get the whole question there?
Yes,
It's really back to the economics,
that's a
isn't
good
it?
question and a
Yeah,
fair one. I just barely touched on it in my first remarks.
sure.
But the issue is that at the end of the day, most of the applications that people are really going to be interested in are going to be real time, as in the drone example, and and people, frankly, are not going to want to be shipping all of their data to a data center. What they're going to want is something that they can run locally, whether it's literally on a computer that they've got in their closet in order to be able to do computation. I've got friends that do that already with LLMs, and or the real-time types of applications. So one of the primary issues is that instead of the sort of the current paradigm where the data centers are actually running both learning and inference, you essentially send out the inference. You send out the some type of I'll call it maybe perhaps a compact model of an LLM to somebody who can purchase it or whatever and run it locally. And what that does is it takes away a lot of it would take 80% of the load that is now being used in terms of the data centers. And so that means that you actually don't need as many data centers and you don't need as much energy for those data centers. And that's where I'd say the power efficiency of a lot of these in-memory computing systems take over, because you're using them in a local real-time environment. The other issue, of course, is in terms of not sharing your data. You send if you send all of your data off to a data center somewhere, who knows what they're going to do with it, honestly, and who else is going to have access to it. People don't want to do that. They want their data, and they want to be able to work on their data privately, and that is going to allow what I'll call democratization, and the ability to have some confidentiality over your data, and know that it's not being just shared with anyone and everyone who you might not actually want to have access to it.
Yeah, and using fewer Hoover Dams worth of energy in the process.
Well, I mean, yeah, I mean, certainly having less Hoover Dams worth or power station issues to fuel centralized data centers, but at the same time, there will have to be more ability to work with dispersed systems. So rather than having, I'll call it concentrated power centers, it would be more dispersed. So clearly there's still going to have to be increases in power supply, but the fact that it's more uniformly dispersed is actually very helpful.
Yeah. Okay. No, thank you for that. Kaushik, I wonder if I can bring you back into the discussion here with a question from Shulpan, which is I thought as an electronics graduate myself, I find utterly fascinating, and I'm paraphrasing a bit here, Shulpan. So I'll try and reflect your question as best I can. But the gist of this question, Kaushik, is that you think about biological vision systems, like whether it's insects or humans, and there's a whole load of pre-processing and data compression that goes on, for instance, in vision systems in the retina itself. And the question really is, what are the analogs, if any, in electronics? In say CMOS architectures and what have you, for what goes on actually in like right now in my retina. How is that, if it can be at all, being replicated in silico, as it were?
Yeah, that's a good question, actually. In fact, in a lot of cases, you don't want to send humongous amount of data for processing. So if you can actually have some computing in the sensor itself, and that's quite useful. In a lot of ways, if you really think about the DVS camera, it's kind of like doing that, a little bit of processing ahead of time, right, to be able to say, hey, if there's a relative motion between the object and the camera. So you can put certainly some processing in there so that you can actually send the relevant data over. You can, as an example, you can potentially say, hey, I'm not interested in everything. I'm only interested in the edges. So you can do some processing of the edges in your sensor itself with very little circuitry, and then you can send the data over. So there are different possibilities, and that's a good point. I mean, we can reduce the computation, send only relevant data as required over to for processing. Yeah, absolutely.
Okay. Yeah, no, lovely, thank you. And in fact, I've kind of got a related question here as well for Arijit. Because basically, as you can tell, I'm mildly obsessed with just trying to reduce as much as possible what goes on the chip. How can we do that? And clearly, I'm not alone in wondering that. Well, there's a question here. How can we shrink or even get rid of analog to digital conversion in analog AI chips? They don't take up 80% of the space, because it was only researching this issue, Arijit, when I was reading around it, and I was really struck by how much of the space on chip is taken up by ADC. So yeah, how can we shrink it?
So ADCs for interfacing with sensors, like external sensors, you mean, or ADCs?
Yeah, I think so, or really in any sort of context. Yeah, and I guess it is
data
context
converters.
dependent.
Yeah.
Yeah.
So a couple of things. I think let me start with the let's pick camera as an example. So if you look at the camera pipeline itself, I mean the world is analog. So everything that you're sensing is going to be analog. So you need an analog to digital converter. One thing that you can think of is the resolution that you need for the ADC may not be 8 bits or 6 bits. You can potentially live with a lot, an ADC with a lower resolution, because many of these AI algorithms don't necessarily need 18-bit or 16-bit of computation. They can work with, particularly on the inference, with lower bits of precision, and your ADC design can be matched with the pipeline that you actually want to design. So one of the mistakes, that as a designer people would often make is to build an ADC which is over provisioned. You don't necessarily need that kind of an ADC that you plug in from somewhere else that may be sensing something which really requires that kind of fidelity into an image processing pipeline, which may only require 4 bits or 8 bits of precision. So that's one thing that that we have to make sure that the ADC is designed for that particular application. The other aspect of this, and that I'm going to say, is many of these control applications, don't necessarily need very high speed ADCs as well. So you can kind of, relax some of the constraints of the ADC as well. And finally, when we look at the in-memory compute, we have seen interesting research work where people have been able to build structures without ADCs, including in Kaushik's group, like ADC-less in-memory computing architectures, which are essentially heavily quantized. So again, understanding the algorithms and understanding that ADCs are expensive, but the way that the semiconductor industry has built ADCs in the last 30 years, it is not necessarily the way you want to build ADCs for neuromorphic or AI applications is important. And we have to make sure that the ADC is designed for the application in mind, which in many cases does not require a very high, what we call ENOB, or the effective number of bits, which actually can lead to very high energy efficiencies as well.
Okay.
Gareth, if I may, can I come back
Please
to the
do,
previous
yes.
question? I mean, absolutely agree with Arijit in terms of the ADC, requirements you can potentially do without even having ADC in some cases, but that would require training. are really understanding the hardware when you do the training. But I just wanted to go back to the eye, the question regarding the eye. The eye does a few other things which we actually can take advantage of, right? It actually has the cones and rods, right? So we can do foveation, right? We can actually focus on a certain area. And our glimpses are actually quite important in recognizing objects, right? So if you can use glimpse-based processing like that, and along with the saccades, which are rapid eye movement, that we have to figure out, hey, what objects are around it, you can actually reduce computation, and you can actually have a more robust system. Just wanted to mention that too.
Yeah, no, I'm glad you mentioned that, and it keeps us on that biologically inspired theme as well. So what I'm going to do now is shift it on a little bit to some benchmarking as well, because we've heard in the talk some striking results about the energy savings from using, for instance, spiking neural networks. So Tanvi, let's just give this one to you, see how you go with it, because I'm just interested in how we get good benchmarks on this when we're comparing the performance, like in energy consumption between the ANNs and SNNs, for a given edge AI task. How you even compare them and what frameworks you have for knowing which is doing the best job.
Right, yeah. And this becomes an even important question because most of the industry focuses on ANNs. And if we really want to include SNNs in future architects, we need to benchmark and show that they actually perform competitive to ANNs or in fact better for some applications. So in my opinion, the best way for this would be to include the already existing benchmarks and get the performance of SNNs on them. And one of the most standardized way that industry follows is MLPerf benchmarks. So there are different MLPerf benchmarks for, say, TinyML, for inference, for training, for client. So, and there, say for training, it only measures how much time it takes to train that particular model. And if you are able to achieve the same accuracy on the given data set. For inference, again, it would measure something like how many tokens you can generate per second. Since these metrics are standard metric, it doesn't matter whether you are using ANNs or SNNs. So if SNN can also achieve the same tokens per second as ANNs can, we can actually show that they are better. And in fact, in these MLPerf submissions, there is a closed category and an open category. So in an open category, you can also change the current algorithm. So we can modify the algorithm such that it is more tailored towards SNN kind of processing and show that it achieves the same accuracy while, say, giving a higher throughput on whatever SNN tailored hardware we have. And I think once that is shown, industry would actually see the potential benefits of these techniques.
Yeah, no, that's lovely. And it moves us very nicely on to, the idea of learning algorithms for SNNs. And a question to, I think I'm going to address this to Kaushik, but any of you can jump in. But Kaushik, let's start with you with this one from Mahima, who says, Professor Roy spoke about a spiking neural network plus, about a spiking neural network plus recurrent neural network model. What types of learning algorithms are used for the spiking neural network component in that model?
Yeah. So again, I mean, going back to, should I use spiking neural networks and where does it make sense to use spiking neural networks? It really depends. I mean, if you really think about the DBS camera example as and if you're trying to do, for example, things like estimation of motion, it does make sense to use spiking neural networks, and you can actually use it to come up with really very, lightweight networks to do, for example, in fact, estimation of speed. And we have done that, where just a one layer of spiking neural networks with proper leak and training for that properly does give you, actually, you can figure out the speed of those networks, of those objects. Now, one other thing to notice is that the difference between, if you really think about the difference between a spiking network and a standard ANN, you actually have a membrane potential, which can actually remember the past, so to say. And so what one can also do is come up with hybrid networks with the first layer of the network could be spiking. It doesn't have to be all layers. You can actually take the best of both worlds in training and inference by having one layer of the network to be spiking. Now, that's also possible. So there are different possibilities, different kinds of applications, but I'm not going to say that, hey, for these large language models, do you use spiking networks? But there are applications where it does make sense to use spiking, where you can potentially use sparsity, get a good amount of improvement in energy consumption, but not everywhere. But in a lot of cases, it doesn't have to be either spiking or non-spiking. It could actually be a combination and a hybrid network that potentially does a job. And as I was showing in case of optical flows, and Orijit was actually showing some, parallel networks that you can have spiking and non-spiking can potentially give you the kind of things that you want at much higher energy efficiency, but not everywhere.
Yeah. Okay.
And training for them is actually a little more difficult to say.
Oh, really? Oh, just in a few, like in a sentence, how is it more difficult?
Because you have to back propagate in this particular case in time.
Okay. Yeah.
And
yeah.
in fact, if you also look at, for example, the activation function, the activation function being leaky integrated fire as an example, is not differentiable everywhere. So you have to make some approximations.
Okay, cool. All right. Now, another big aspect of this story that we haven't touched on so far in this discussion is the stochastic element. And another surprise to me, really, coming into this field, having studied years ago and not realizing how things have moved on, but just the efficiencies that can come about from stochastic, from randomness, basically. So I'm going to put this one to you, Stan. And the question really is, can the nonlinear dynamics and chaos found in nanoscale devices be harnessed to unlock novel cognition capabilities in future AI hardware?
Definitely. You see in some types of algorithms that people are running now is that they're essentially doing deterministic calculations, but then they're going off and running a random number generator in order to create some stochastic input in order to help a network converge to an answer. Whereas instead of having to actually calculate random numbers, which is actually a very expensive and time-consuming operation, you can utilize the stochastic properties of devices in your system. And so, for instance, in something like a Hopfield network, I mean that's an issue where you have effectively an energy minimization type of operation in which you are trying to find a global minimum in a multidimensional, highly non-linear space, and it turns out that if your hardware that you're using to operate the Hopfield network has literally noise in it, that actually helps the system find the global minimum naturally without having to do a lot of other computation on the side. So this ability to actually harness the stochastic nature of nano devices is actually a significant opportunity for a set of AI types of systems.
Yeah. Okay. Which does bring us very neatly and conveniently onto the future as we wrap up in the final few moments of this session. So I'm going to ask each of our speakers just to give us like a minute or so on where they see the future in this whole field. So Kaushik, seeing as we heard you right at the beginning, why don't you take this as well? The future, according to Kaushik, and yes, we will invite you back in 30 years and hold you to account for your answer.
Um, Thanks, Gareth. You know, looking at the models becoming larger and larger, and our insatiable demand for these new applications, um, and looking at the basic computation elements that you need for AI. I think the memory-centric architecture, which is flexible, and and then you can put things on a substrate, and you can actually have different kinds of chiplets coming from different people doing different kinds of acceleration, having possibilities of compute in memory in each of those levels of the memory hierarchy, and having, again, as we mentioned, that it doesn't have to be, the compute doesn't have to be in the register files or the L1 caches, L2 caches. It could be in the DRAMs, could be even other kinds of memories, right? So an architecture like that, where you're able to map your algorithms very effectively in such an architecture for energy efficiency, is what I feel is going to be the future.
Okay, all right. Arijit, how about you? The future.
Future, so easy to predict, isn't it?
If
So
only.
I'd say that, like if you kind of took a snapshot of the world 20 years back, I'd say 20 years back, most of us, including myself, would have thought that the future of AI would look like flying cars, humanoids, robots, and all of that, right? So instead, one of the first things that AI learned to do was write poems, right? You look at language models as the first thing that they did. It was not anything that anyone was expecting. So I feel like it's always a good reminder that we always don't know what the future is going to look like, and that's a part of what makes it exciting. I mean, as you see AI evolve, I'm kind of also, I've been thinking about it for a while, that it also makes you pause and think about intelligence overall and creativity and what it means to be creative, and I think more profoundly what it means to be human, because many of the attributes of human intelligence can now be modeled. It also makes you wonder what being human means. So I'll
Yeah,
be
it does.
excited for the next 30 years. I'm not going to come back in 30 years, but
Yeah. Okay. Well, that's a very philosophical answer. So, Tanvi, are you equally philosophical as you assess the future?
So if about the future, yeah, definitely I agree with both Professor Ajit and Kaushik Roy. But from the hardware perspective, I feel the near future will be heterogeneous systems. Systems that include both the traditional architectures as well as memory-centric architectures. The reason I feel this is going to be the future is because we have built these billions and trillions parameters large language models. And part of that, especially the decode stage, is memory bound. So, given that we are going from the age of scaling to the age of thinking, which actually requires reasoning and a high context length for during inference, we are more focused on having a larger memory capacity and doing the compute near memory. So that is why I feel we'll have systems that will include both memory centric and traditional. Now, how the memory centric architecture will look like is going to be interesting, whether it is going to be DRAMs or using
Yeah.
these
But
ENVMs or something else. Yeah.
sure. But you'll be one of the ones designing it. That's what's so exciting. It's having just been awarded in the last your PhD last year, your PhD. Right, Stan, finally, from you. The future according to Stan, then, people.
Well, I've actually been working in this area since 1995. So I have a 30-year perspective on it. And what I can tell you is that I could not have predicted anything that it's been going on right now when I first started in this area. I mean, it's been one surprise after another, and I think that's really what we're going to be seeing. I did mention that we're in this, right now, we're finally in an era of let a thousand flowers bloom. There are over 10,000 papers published every year now just on the topic of memristor, just that one topic. Uh, uh, no one can actually, you know, pull all of that in and understand it. So there's going to be a lot of false starts, a lot of competition, which is going to be good. But how long this is going to take to actually finally come up to what I'll call a solution to the problem. I don't really know. I mean,
Right.
it could take
Okay.
a decade or two.
It could take a decade or two, says Stan at the end. Well, thank you so much for rounding that up for us. Today we've heard from Kaushik Roy, Arijit Ray Chowdhury, Tanvi Sharma, and of course Stan Williams, we just heard there. Thanks to them and thanks to you for being here. But don't be a stranger, folks. Do visit the Frontiers in Science website to read the article we've been discussing and, of course, all the related content on the Article Hub. You can continue the conversation on social media using the hashtag FrontiersIn. And don't forget to subscribe to our Frontiers in Science updates and visit the Frontiers Forum website for upcoming events. For now, though, from me, our guests, and the entire brilliant team at Frontiers who put this together, thank you, experts, and most of all, thank you for joining us. Take care. Bye-bye.